Rutherford's discovery of the nucleus, the birth of modern atomic physics. In the early 20th century, scientists believed they understood the basic structure of the atom. The electron had been discovered, and physicists had developed models to explain atomic structure. Yet between 1908 and 1911, an experiment in Manchester, England would completely overturn these assumptions and reveal a reality so unexpected that even its discoverer initially found it difficult to believe. Ernest Rutherford's discovery of the atomic nucleus fundamentally transformed our understanding of matter and opened the door to the nuclear age, the plum pudding model. To appreciate Rutherford's revolutionary discovery, we must understand the prevailing atomic theory of the time. J.J. Thomson's discovery of the electron in 1897 proved that atoms contained smaller charged particles. This raised a crucial question. If atoms contained negatively charged electrons, how were they structured? And where was the positive charge that made atoms electrically neutral? Thomson proposed what became known as the plum pudding model. In 1904, he suggested that atoms consisted of a sphere of positive charge with electrons embedded throughout, like plums in a pudding. The positive charge was thought to be spread uniformly throughout the atom's volume. This model had intuitive appeal. It explained electrical neutrality and seemed to account for atomic stability, though it struggled to explain certain phenomena, particularly atomic spectra. Thomson's model represented the scientific consensus as the new century began. Ernest Rutherford, background. Ernest Rutherford was born in 1871 in rural New Zealand. Through scholarships and exceptional ability, he reached Cambridge University, where he studied under J.J. Thomson at the Cavendish Laboratory. Rutherford quickly established himself as an exceptional experimental physicist, particularly in investigating radioactivity. His early work was groundbreaking. He identified and named alpha and beta radiation, showing that radioactive decay involved elemental transformation. In 1908, he won the Nobel Prize in Chemistry for his work on radioactive substances. By 1907, Rutherford had moved to the University of Manchester, where he established a thriving research laboratory. Working with Hans Geiger and Ernest Marsden, he would make his most famous discovery. Rutherford had a remarkable ability to design elegant experiments that tested fundamental questions, and he fostered an environment encouraging bold thinking and meticulous experimental work. The gold foil experiment, the experiment that revolutionized atomic physics, began almost accidentally. Rutherford and Geiger had been studying how alpha particles scattered when passing through thin metal foils. Most alpha particles pass straight through with little deflection, consistent with Thomson's plum pudding model. In 1909, Rutherford suggested that Ernest Marsden, a young undergraduate, investigate whether any alpha particles scattered at large angles. Rutherford didn't expect much. It was meant as a training exercise. What Marsden found was astounding. The experimental setup was relatively simple. A radioactive source emitted alpha particles toward very thin gold foil, only a few atoms thick. Scattered particles were detected by a zinc sulfide screen, producing tiny flashes of light when struck. These scintillations had to be counted by eye in darkness, tedious work requiring extraordinary patience. Marsden observed that while most alpha particles pass through with minimal deflection, a tiny fraction, about 1 in 8,000, bounce back at large angles, some completely reversing direction. This was utterly unexpected. Rutherford later described his reaction vividly. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. The revolutionary conclusion. The large angle scattering Marsden observed was completely incompatible with Thomson's plum pudding model. In that model, the diffuse positive charge couldn't produce the violent deflections observed. Alpha particles, being massive and fast-moving, should pass through with only slight deflections. Rutherford spent months working through the mathematical implications. He considered various explanations. Multiple small angle scatterings adding up to large deflections proved impossibly improbable. Unknown forces seemed like unnecessary speculation. By 1911, Rutherford reached a radical conclusion. The only explanation for large angle scattering was if the atom's positive charge wasn't spread throughout its volume, but concentrated in an extremely small, massive core at its center. When an alpha particle passed very close to this core, electromagnetic repulsion between positive charges would be enormous, easily enough to deflect or reverse the particle's direction. Rutherford called this dense, positive core the nucleus. His calculations suggested it was incredibly tiny, about 10,000 times smaller than the atom itself, yet contained virtually all the atom's mass. The rest was mostly empty space through which electrons somehow moved. Implications and impact. Rutherford's nuclear model was profoundly counterintuitive. Atoms were almost entirely empty space. If an atom were scaled to a football stadium's size, the nucleus would be about pea-sized at the center, with electrons orbiting in the distant stands. This model immediately explained the experimental results. Most alpha particles passed through empty atomic space, experiencing only minor deflections. Occasionally, a particle would pass close to a nucleus, experiencing intense electromagnetic force and dramatic deflection. Rutherford published his model in May 1911 in the Philosophical magazine. The paper combined experimental evidence, mathematical rigor, and physical insight. His equations predicted exactly how many particles should scatter at each angle, matching observations with impressive precision. However, the model faced a serious theoretical problem. According to classical electromagnetic theory, orbiting electrons should constantly emit radiation and spiral into the nucleus instantly. Atoms should be unstable, yet weren't. This paradox wasn't resolved until 1913, when Niels Bohr proposed his quantum model incorporating emerging quantum mechanical ideas. Legacy. The nucleus discovery transformed physics and chemistry. It explained the periodic table's patterns and chemical bonding nature. It revealed that radioactivity involved nuclear changes. Most importantly, it showed the nucleus contained enormous energy in a tiny volume, energy that might be released, leading eventually to nuclear power and weapons. Rutherford's discovery exemplified the scientific method at its best. A carefully designed experiment produced unexpected results. Rather than dismissing anomalous data, Rutherford followed evidence wherever it led, even contradicting established theory and common sense. He proposed a new model explaining observations and making testable predictions. Ernest Rutherford died in 1937, buried in Westminster Abbey near Isaac Newton, fitting recognition for his fundamental contributions. The discovery of the nucleus remains a perfect example of how experimental science progresses. A simple experiment revealed profound truth about matter structure. That truth seemed absurd, yet evidence was undeniable. From that discovery flowed much of modern physics. Today we take the nuclear model for granted. Yet just over a century ago, it was radical, born from curiosity, careful experimentation, and one scientist's willingness to believe the evidence, however incredible. That spirit of inquiry remains the heart of scientific discovery.